Good day, everybody. How are you all doing? Today, we are going to talk about energy transfer in thermodynamics. So, here I go. So, this chapter is on energy transfer. Okay. So, here we take the entire room, including the air and the refrigerator or fan. Okay. As a system, which is an adiabatic closed system since the room is well sealed and well insulated. The only energy interaction involved is the electrical energy crossing the system boundary and entering the room. As a result of the conversion of electrical energy consumed by the refrigerator, in this case, to keep the room cold, the air conditioner cold, the room temperature will rise. Why the room temperature will rise? Because the energy is consumed to run a motor and everything for the refrigerator, and therefore the room temperature will rise. So the figure is on a refrigerator operating with its door open in a well sealed and well insulated room. A fan running is a well sealed and in a well sealed and well insulated room will also raise the temperature of the room. Why? Because electrical energy is used to run the fan. Energy can exist in numerous forms such as thermal, mechanical, kinetic, potential, electrical, magnetic, chemical, and nuclear. And their sum constitutes the total energy, capital E, of the system. Thermodynamics only deals with change of total energy. Macroscopic forms of energy, those a system possesses as a whole with respect to some outside reference frame, such as kinetic and potential energy. Microscopic forms of energy, those related to the molecular structure of a system and the degree of the molecular activity. And what is the internal energy U? The sum of all microscopic forms of energy. This figure, at least six different forms of energy are encountered in bringing power from a nuclear plant to your home: nuclear, thermal, mechanical, kinetic, magnetic, and electrical. So first you have the power plant where you heat the steam, water, or boil the water to generate steam. How do you boil the water? You use nuclear rods. Okay. And so nuclear energy is involved, thermal energy because you are heating the water, mechanical energy because you use the power of the steam, you compress the steam, and you run a turbine, basically. What is a turbine? Basically, brushes rubbing against uh, steel surface, fixed steel surface at a high speed, generate static electricity. Okay. And then it is converted to electrical energy. Okay. And the kinetic energy comes from the movement of water molecules. And when electrical energy is generated, it is basically electromagnetic waves. So magnetic energy is also there. And of course, electrical energy. And then it is delivered to your home, from where it is delivered to the outlet, power outlet in your room. Kinetic energy is the energy that a system possesses as a result of its motion, okay, relative to some reference frame. And potential energy, the energy that a system possesses as a result of its elevation in a gravitational field. The macroscopic energy of an object changes with velocity and elevation. Velocity is the speed at which it is moving. The difference between speed and velocity is velocity as a direction to elevation is the elevation of the object, how far it is or how much above the sea level. These are the different equations for kinetic energy, then specific kinetic energy per unit mass, potential energy per unit mass, total energy. U is the internal energy, remember, plus kinetic energy plus potential energy. Then you divide by the mass, you get energy of a system per unit mass. Okay. And energy flow rate, E dot. Remember, the dot on the top gives you the flow rate. So E dot indicates, capital E dot indicates the energy flow rate. In this case, M dot is the mass flow rate. So here is a picture. It's a cylinder. It has an area of pi d square by 4 cross-sectional area. And m dot is the mass flow rate, which is rho density multiplied by velocity average multiplied by cross-section. And steam is flowing through it, and total flow of energy, E dot, is m dot mass flow rate times E dot mass flow rate is given by the above equation multiplied by the specific energy. Okay. And the units are, mass flow rate is in kilograms per second, energy flow rate is in kilojoules per second, which is also equivalent to kilowatt. Some physical insight to internal energy. We have sensible energy, latent energy, chemical energy, and nuclear energy. Sensible energy is a portion of the internal energy of a system associated with kinetic energies of the molecule. Latent energy, internal energy associated with the phase of a system, such as water, liquid phase, vapor phase, okay, solid phase. Chemical energy, internal energy associated with the atomic bonds in a molecule. In water, you have the dipole bonds between hydrogen molecule and oxygen molecule. And then you have the nuclear energy, the tremendous amount of energy associated with the strong bonds within the nucleus of the atom itself. Okay. Then you have thermal energy, which is sensible plus latent energy, and internal energy is sensible plus latent plus chemical plus nuclear. Okay. Internal energy of a system is the sum of all forms of microscopic energies. The total energy of a system can be contained or stored in a system and thus can be viewed as static forms of energy. The forms of energy not stored in a system can be viewed as the dynamic forms of energy, okay, or energy interaction. Dynamic means moving. The dynamic forms of energy are recognized at the system boundary as they cross it, and they represent the energy gained or lost by the system during a process. The only two forms of energy interaction associated with a closed system are heat transfer and work. The difference between heat transfer and work: an energy interaction is a heat transfer if its driving force is a temperature difference. So remember, uh, energy interaction is heat transfer. That means heat transfer occurs because there is difference in temperature between two places, right? Otherwise, it is work. So heat work is also energy transfer. Heat transfer is also energy transfer, but heat transfer occurs because difference in temperature between two places. The macroscopic kinetic energy is an organized form of energy and is much more useful than the disorganized microscopic kinetic energy of the molecule. Okay, so microscopic kinetic energy of molecule does not turn the wheel. However, the macroscopic kinetic energy of the dam, this is a water dam, will rotate the water wheel and generate the macroscopic kinetic energy is converted into power by the turbine or the rotation of the turbine. Okay. So please do not quit right away. I'll give you some important hint or tip at the end of this program. And please subscribe to my channel by hitting the red subscribe button at the bottom right corner. More on nuclear energy, the best known fission reaction involves the split of the uranium atom U-235 isotope into other elements and is commonly used to generate electricity in nuclear power plants, to power nuclear submarines and aircraft carriers, and even to power spacecraft as well as building nuclear bombs. So basically, U-235 Isotope fission means breaks up into other elements and releases energy, and that energy is used to heat up water in a power plant to generate steam. That steam runs a turbine. The turbine blades rotate against some metal surface, generate static electricity from which our electrical current is produced. Nuclear energy by fusion is related when two small nuclei. Difference between fission and fusion, as you understand, is combined. Okay, nuclear energy when two nuclear so nuclear energy by fusion is released when two small nuclei combine into a larger one. The uncontrolled fusion reaction was achieved in the early 1950s, but all the efforts since then to achieve controlled fusion by massive lasers, powerful magnetic fields, and electric currents to generate power have failed. So that's why fusion is not used in nuclear power plants, only fission type of nuclear reaction is used. And here basically they're explaining the difference between a fission and a fusion. Okay. Here they're showing only you the fission of urium, the breaking of urium into smaller parts and releasing energy. So mechanical energy, the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. So kinetic energy and potential energy is given by this formula per unit mass. It's small letter as you see, E mechanical energy. First one is pressure energy, next one is kinetic energy, next one is position energy or potential energy. And when you multiply by the mass flow rate, you get the total energy flow, rate of mechanical energy of a flowing fluid. Mechanical energy changes of a fluid during incompressible flow is given by delta E mechanical, which is change in pressure, change in velocity, and change in height or change in position. And again, rate of mechanical energy change, you will multiply it by the mass flow rate, m dot. Mechanical energy is a useful concept for flows that do not involve significant heat transfer or energy conversion, such as flow of gasoline from an underground tank into a car. Is it? Okay. Mechanical energy is illustrated by an ideal hydraulic turbine that coupled with an ideal generator. In the absence of irreversible losses, the maximum product power is proportional to the change in water surface elevation from upstream to the downstream reservoir in B. So it is at position A, it falls to position B, change in potential energy, or the drop in the that was in part A on the left. In part B, they're showing you drop in water pressure from just upstream to downstream of a turbine. Okay. Heat, the form of heat energy that is transferred between two systems by virtue of temperature difference. Energy can cross the boundaries of a closed system in the form of heat and work. Remember that system boundary, heat can transfer, work can transfer around, through the boundary, both in and out. And temperature difference is driving force in for heat transfer. The larger the temperature difference, the higher is the rate of heat transfer. Heat transfer per unit mass is given as small q. Total heat transfer, capital Q, divided by mass, it's kilojoule per kilogram. Amount of heat transfer when heat transfer rate is constant. You're basically taking the time derivative from T1 to T2, okay? And amount of heat transfer when heat transfer rate changes with time. So you have Q dot time multiplied by delta T. Q dot is the rate of change of heat transfer, or change of heat transfer with time multiplied by total change in time. Okay, so they're showing the example with a baked potato example. Okay. So during an adiabatic process, system exchanges no heat with its surrounding. Okay. So because it is well insulated, and when you put 30 kilojoules in heat, basically mass is 2 kilogram, 10 time is 5 seconds. So 6 kilowatt, Q dot is 6 kilowatt. How do they get it? 30 kilojoule divided by 5 second is 6 kilojoule per second or kilowatt. Okay. And Q is 15 kilojoule per kilogram. Q is specific heat or change in heat per unit mass. So it is 30 kilojoule divided by 2 kilogram is 15 kilojoule per kilogram. Historical background on heat, caloric theory, it asserts that heat is a fluid-like substance called the caloric, that is massless, colorless, odorless, and tasteless substance that can be poured from one body into another. Kinetic theory, theme treats molecules as tiny balls that are in the medium and thus possess kinetic energy. Heat is the energy associated with random motion of atoms and molecules. Okay. Heat transfer occurs by three types of mechanism: conduction, convection, and radiation. Conduction is transfer of energy from the more energetic particles of a substance to the adjacent less energetic ones as a result of interaction between particles. Okay. Convection, transfer of energy between a solid surface and the adjacent fluid that is in motion. So convection has a motion in it, and it involves the combined effects of conduction and fluid motion. And radiation is a transfer of energy due to emission of electromagnetic waves or photons. Okay. No conduction, no convection. Here, energy is transferred through emission of electromagnetic waves. What is work? The work is the energy transfer associated with the force through a distance. Okay. A rising piston, a rotating shaft, and an electrical wire consist of the system boundaries and are all associated with work interaction. Formal sign convention, heat transfer to a system and work done by a system are considered positive, whereas heat transfer out from a system and work done on a system are negative. Okay. Alternative to sign convention is to use subscript in and out to indicate direction. Okay. So work done per unit mass is kilojoule per kilogram is 30 divided by uh, 2 will be 15 kilojoule per kilogram. Whereas workflow will be 30 kilojoule divided by 5 second is 6 kilojoule per second or 6 kilowatt. Heat versus work, both are recognized at boundaries of a system as they cross the boundaries, that is, both heat and work are boundary phenomena. Okay. System possesses energy but not heat or work. Both are associated with a process, not a state. Unlike properties, heat or work has no meaning at a state. Both are path functions. That is, their magnitude depends on the path followed during a process as well as the end states. Properties of point functions have exact differentials, like they're showing the change in volume, and that is delta V. Path functions have inexact differential. Notice the difference. One is dV, another is delta. Okay. And they have inexact differential. And notice how the work is written. You're not writing V12, volume 12. You are writing delta V. Whereas for work, it is written as W12 to indicate that it depends on the path. Here, the path is from 1 to 2 position. Properties are point functions, but heat and work are path functions. Their magnitudes depend on the path followed. Okay. So delta V, okay, volume change, okay, in path A is from 5 is the final, minus 2 is 3 meter cubed. Delta V, volume change in process B, is also same 3, because volume is a state function, not path function. Whereas work on path A, or process B will be different. Electrical work is given as Vn, okay? And flow of electrical energy, V is voltage, okay? Flow of electrical work, We dot, is given as volt, V multiplied by current. Electrical power is measured in watt. When potential difference and current changes with time, We is equal to what is the total amount of work done, electrical work done, is 1 to 2 VI dt, kilojoule. Okay. When potential difference and current remains constant, then it is VI is taken outside the integral, and we have for dt delta t. Okay. T is time here. So the formula for We dot, or the flow of electrical energy, is V square by R, or I square R, is commonly known as Joule work. There are two important requirements for a work interaction between a system and its surrounding to exist. There must be a force acting on the boundary. The boundary must move. The work done is proportional to the force applied and the distance traveled. Okay. So distance traveled in this case is S. Okay. And work is dependent. Remember, work is a path function, so it depends on the path taken between position 1 and position 2. It's force multiplied by change in distance. Okay, ds is change in distance. Shaft work is given as torque F times R. F is equal to, from that we derive F is torque divided by arc. S, what is S? It's 2 pi r n. 2 pi r is the circumference of the circle that is moving, multiplied by n. N is your number of times that it is rotating. So work is force times distance, which is force is torque divided by r, multiplied by S is 2 pi r n. So ultimately it becomes 2 pi n t is the shaft work. Okay. The power transmitted through a shaft is the shaft work done per unit time. Okay. So basically 2 pi t is the torque, 2 pi t, these are constant, n dot is the change in rotation per unit time. Okay. N is the number of rotations. Both energy transfer to rotating shaft is commonly encountered in practice. Spring work, similarly, delta W spring, change in work of the spring. Notice it is written as delta W because it's a path function. It's F turn dx. F is the force acting, dx is the change in position. So for linear elastic spring, the displacement x is proportional to the force applied. So F itself is kx. So work spring becomes half. K is a elasticity constant multiplied by x2 square minus x1 square. x1 and x2 are the initial and final displacement as shown in the diagram. The displacement of linear spring doubles when force is doubles. Okay. Solid bars behave as springs under influence of a force. Okay. So work done, elastic work done is force times dx, your change in position. The force is written as sigma A times capital A is the pressure, shear pressure. Sigma n is the shear pressure, which is the force per unit area, multiplied by A is the cross-sectional area, multiplied by the distance displaced. Okay. So here they're showing work associated with stretching of a liquid film. I will not go into the details on this. The work done to raise or to accelerate a body, the work transfer needed to raise a body is equal to the change in potential energy of the body. Okay. The work transfer needed to accelerate a body is equal to the change in kinetic energy of the body. The figure shows the energy transfer to a body while being raised is equal to change in its potential energy. So non-mechanical forms of work is electrical work, magnetic work, and electrical polarization work. Electrical work, the generalized force is the voltage, and the generalized displacement is the electrical charge. Okay. Magnetic work, generalized force is the magnetic field strength, and the generalized displacement is the total magnetic dipole moment. Okay. Similarly, you have electrical polarization work. First law of thermodynamics, conservation of energy principle provides a sound basis for studying relationship among various forms of energy and energy interactions. The first law states that energy can be neither created nor destroyed during a process. It can only change forms. First law for all adiabatic process. Remember, adiabatic process, no heat transfer between two specified states of a closed system. The net work done is the same regardless of the nature of the closed system and the details of the process. So bottom line, energy cannot be created or destroyed. Okay. It can only change forms. The energy, potential energy of the rock at the top of the hill is 10 kilojoule. It does not have kinetic energy, but when it keeps dropping, okay, say it has dropped a little, some height, then its potential energy changes from 10 kilojoule to 7 kilojoule because the change in position, and the kinetic energy because of the gain in motion of the rock is now 3 kg instead of 0 kg at the top. The increase in energy of a potato in an open oven is equal to the amount of heat transferred to it. In the absence of any work interaction, the energy change of a system is equal to the net heat transfer. Okay. So initially it had 15 kilojoule, 3 kilojoule is leaves the system, so 12 kilojoule is what is left is the change in energy. Okay. Work of electrical done in an adiabatic system is equal to the increase in energy system. So uh, let's see. So in a battery, current flows from, as you can see, from negative, or electrons flow from negative cathode to the positive anode. Okay. And 5 kilojoule is transferred by the battery to the adiabatic room. Similar idea over here. One is a rotating shaft, another is a moving piston. So energy balance is energy in minus energy out is equal to total change in energy of the system. And then change in internal energy is equal to total change in delta U is equal to mass times position U2 minus U1. And change in kinetic energy is half mv2 square minus v1 square. 2 is the final position, 1 is the initial position. Similarly, change in potential energy is m times g, which is constant, multiplied by the change in height. Okay. So energy change is energy at final state minus energy at initial state. And delta E, change in energy of a system, is equal to E2 minus E1. And what is delta E? Is change in internal energy plus change in kinetic energy plus change in potential energy. For stationary systems, delta kinetic energy is equal to delta potential energy is zero. Nothing changes. So change in energy is change in internal energy in this case because nothing is changing. Position is not changing. Velocity is not changing. So what are they doing here? They're doing energy balance for any system undergoing any kind of process can be expressed more compactly as E in minus E out is a change in energy of the system. Rate form dividing by time, E dot M in minus E dot out is equal to delta E system. Rate in change, okay? Rate change. For constant rates, the usual total quantities during a time interval are related to the quantities per unit time, okay? So change in energy is d by dt, change in energy per unit time multiplied by total change in time. Energy transfer expressed in per unit mass basis is the same. Small e in this case, E in minus E out is equal to delta E, which is obtained by dividing all quantities in the previous equation by the mass. Energy balance can be expressed also in differential form. Delta E in minus delta E out is equal to dE system. Okay. The mechanisms of energy transfer, heat transfer, work transfer, and mass flow. Okay. So in 247, the energy content of a control volume can be changed by a mass flow as well as by heat and work interaction. Okay. And for a closed system cycle, I should say, change in energy is zero. Q is equal to W. Efficiency is one of the most frequently used terms in thermodynamics, and it indicates how well an energy conversion or transfer process is accomplished. Efficiency is desired output by required output. Okay. Efficiency of a water heater, the ratio of energy delivered to the house by a hot water to the energy supplied to the water heater. Okay, so here are some typical efficiencies. So gas, conventional, high typical efficiencies of conventional and high energy electric and natural gas water heaters. Okay, so gas conventional is 55%, high efficiency is 62%. Electric conventional is 19% and high efficiency is 94%. Heating value of the fuel, amount of heat released when a unit amount of fuel at room temperature is completely burned and combustion products are cooled to room temperature. You have a lower heating value when water in the combustion gases is a vapor, and higher heating value when the water in the combustion gases is completely condensed and the heat of vaporization is also recovered. So combustion equipment efficiency is given by this symbol called, you can see it's a Greek symbol, and it's Q useful divided by HV. Q useful is useful heat delivered by the combustion equipment divided by heating value of the fuel burned. Of course, not all heating value of the fuel burned will be converted to useful energy. Some of it will be lost. That's why that efficiency comes in for the combustion equipment. The definition of heating value of gasoline. Uh, so combustion gases, when you burn gasoline, you get carbon dioxide, water, N2, etc. So gasoline, you put 1 kilogram gasoline, 25 degrees centigrade inside the combustion chamber. Also, you supply air, and heating value is 44,000 kilojoule per kilogram of the fuel. The efficiency of space heating systems of residential and commercial buildings is usually expressed in annual fuel utilization efficiency, AFUE, which accounts for combustion equipment efficiency as well as other heat losses, such as heat losses to unheated areas and startup and cool down losses. The AFUE of new heating system is about 85%. Although the AFUE of some old heating system is under 60%. The AFUE of some new heating efficiency furnaces exceeds 96%, okay, etc. So eta is the efficiency overall, is given by eta combustion multiplication product, eta combustion equipment times eta thermal times eta generator. And that is the final equation. A generator, a device that converts mechanical energy to electrical energy. Generator efficiency is the ratio of electrical power output to the mechanical power input. Thermal efficiency of a power plant, ratio of the net shaft work output of the turbine to the heat supplied, heat input to the working fluid. The overall efficiencies are about 25 to 30% for gasoline automotive engines and 35 to 40% for diesel engines and up to 60% for large thermal power plants. And here is lighting efficiency, okay, lumens per watt of electricity. So you can see a fluorescent lamp supplies 15 watts of a compact fluorescent. That's why all the lights today are fluorescent lamps, because they supply same energy as a 60-watt bulb at a lower wattage, lower amount of energy consumed. Using energy efficient appliances conserve energy. It helps the environment by reducing the amount of pollutants emitted to the atmosphere during the combustion of the fuel. The combustion of fuel produces carbon dioxide, nitrogen oxide, hydrocarbons, smog, carbon monoxide, toxins, sulfur dioxide. The efficiency of cooking appliance represents the fraction of energy supplied to the appliance that it transferred to the fluid. So out of 5 kilowatt supplied by the electrical heater, only 3 kilowatt is utilized. So efficiency is 60%. And then it loses 2 kilowatt also. Energy cost of cooking with different appliances. So eta mechanical efficiency is given mechanical energy output divided by mechanical energy input. E mechanical energy out divided by E mechanical in is 1 minus E mechanical loss divided by E mechanical in. Okay. And the effectiveness of conversion process between mechanical work supplied or extracted and the thermal energy of the fluid is expressed by pump efficiency and turbine efficiency. So pump efficiency is given by this formula, mechanical energy increase in the fluid divided by mechanical energy input, and turbine is mechanical energy decrease of the fluid by mechanical energy output. So here they show us how to mechanical energy of a fan. Okay. So mechanical energy is is change in mechanical energy of the fluid, which is change in which is mass flow rate times velocity in the second stage. There is no velocity in the first stage. So V times V2 square divided by 2, okay, divided by what is the shaft work, 50. And you can see, okay, that the mechanical efficiency is less than 1, of course, it's 74%. And these are the different formulas for the different efficiencies for motor, generator, pump, motor combination, and then turbine generator combination. The overall energy efficiency of a turbine generator is the product of the efficiency of turbine and the efficiency of the generator, and it represents the fraction of mechanical power of the fluid converted to electrical power. The conversion of energy from one form to another often affects the environment and the air we breathe in many ways, and thus the study of energy is not complete without considering its impact on the environment. Pollutants emitted during combustion of fossil fuels, that is coal, are smog, acid rain, and global warming. The environmental pollution has reached such high levels that it becomes a serious threat to vegetation, wildlife, and human health. We know the global pollution. Okay. Pollution comes from burning fossil fuels in power plants, also generated by combustion of gasoline in our cars. Ozone and smog. What is smog? Smog is made up mostly of ground level ozone, but it also contains numerous other chemicals, including carbon monoxide, particulate matter such as soot and dust, volatile organic compounds, okay, hydrocarbon and nitrogen oxides. Ozone irritates eyes and damages air sacs of the lungs, where the oxygen and carbon dioxide. Where does ozone come from? Okay, ozone is coming from refrigerants. Okay. Okay. So you can see how smog is formed with the emission coming out from the cars reacts with under the sun's light. Okay, and ozone creates smog. Acid rain is burning of coal. Fuel produces sulfur dioxide because coal contains sulfur. Sulfur dioxide mixes with water in the atmosphere and produces sulfuric acid, which comes down as acid rain. Shows you how sulfuric acid is formed, how acid rain is formed basically. Greenhouse effect. So gas allows the solar radiation to enter freely but blocks the infrared radiation emitted by interior surfaces. So what is happening? A layer of gases surrounds the earth. These gases come from burning of fossil fuels, burning of fossil fuels in power plants, burning of fossil fuels in our car. They form a layer of gas, greenhouse gases that traps the sun's that lets the sun's radiation come in but will not let it escape. And the surface of the earth, which warms up during the day as a result of absorption of solar energy, cools down at night by radiating its energy into the deep space as infrared radiation. Carbon dioxide, water vapor, and trace amounts of some other gases such as methane and nitrogen oxides act like a blanket and keep the earth warm at night because it will not let the heat go away. Result is global warming. So they're saying by 2100 temperature will rise about 2 degrees Celsius. Okay. Storms and so you can already know about the heavy fire damage in Los Angeles area. It is caused by change in global weather patterns. So from uh, the smog produced by the combustion of gasoline, we can use electrical cars, and then there is thermal. Uh, Instead of using fossil fuels, we can use wind turbines to generate electricity. So, what did we discuss? We discussed forms of energy, energy transfer by heat, energy transfer by work, mechanical forms of work. We also discussed first law of thermodynamics. Energy is not created or destroyed, energy remains constant. Energy conversion efficiencies, as we learned, nothing is 100% efficient. Everything has some amount of energy lost from the input energy, every kind of device. And then we talked about or discussed about what is the causing global energy, a global temperature rise caused by the greenhouse gases which surrounds the earth as a layer and does not allow heat to escape as infrared radiation from the earth's surface. It raises the temperature, and they're afraid that by 2100, year 2100, temperature of the earth will rise by 2 degrees Celsius. I will stop here today. If you have any question, comment, write me a note. Please write me a comment. I appreciate that. Please give me a thumbs up if you like this video. If you like this video, share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button. And please do not forget to check my channel every day because I will be back tomorrow with another interesting video. Let YouTube know that you'd like to be notified every time I upload a new video. Thanks for watching, and I look forward to meeting you on my next video. Thanks. Take care. Have a nice day. See, see you. See you. Bye.